and that's great too. But anyway, we're live, and really glad that you're all here. And if you're watching online, also glad that you're doing that. If you are online, you should be able to comment on the stream. And so if you have a question, do that. And somebody, I just want you to do that, trusting that somebody is going to read those to me so that those questions can actually get addressed. And if nobody does that, then you have at least asserted your existence to the internet. You've typed a comment on a YouTube thing, and there are some people who have never done that. So at least you've got that going for you. Anyway, we talked a little bit before we got started about kind of who's doing what with Kafka, and basically this is a fairly experienced crowd. So I have a little bit, in the middle of this presentation, a little bit of Kafka overview, and I will probably skip most of that, since I think most of you are fairly familiar with what's going on. There are still a few points in there that are necessary to hit, because even if you're using Kafka, there are things you might not know. But that's kind of where we are. I want to talk to you tonight, you see the words on the screen, about realizing ACID transactional semantics at scale with Kafka. And the basic outline of what we're going to do is I'm going to set up in terms of a distributed system, in terms of the garden variety distributed systems that most of us are building these days. I'm going to define what in that context. Talk just a little bit about some Kafka things. That's going to be a reminder for most of you, but a little bit of some Kafka features, so we can think about how Kafka might address those. And then we're going to come back in the third part and say, here's the problems that ACID gives you, here's what Kafka does, and here's how you could use Kafka as an architectural element to realize those properties at scale. So this is fundamentally a software architecture talk. Who am I? I forgot that part. My name is Tim. I work for a company called Confluent. Confluent makes an event streaming platform based on Apache Kafka. I run the developer relations team at Confluent, so that means most of the time I type things into Slack and I am on video calls. But sometimes they also let me out of the box to come and do events like this, so I'm very grateful to be here. This is my second time in Israel. I actually get to be here for a few days, and I'm pumped. The second talk is going to be by my colleague. No, I'm just going to let you know. He's going to introduce himself, but he's on my team, and I'm glad that we're here together. All right, this talk is stolen more or less completely from this guy, Martin Kleppmann. It turns out most of the good ideas I have about streaming, sometimes I don't even know, but I come to find out later, they came from Martin. So he is, I think, a tremendously important leader in this space, and because I stole his talk, I wanted to also plug his book and just let you know he's a guy you should be following, because a lot of things he said in the past and probably things he is going to say in the future are important things to know when you're thinking about streaming. With that, if there's anybody, I saw some phones coming out. If you want to take a picture of that, internet, if you want to take a screenshot, internet, actually you can go back later because this is being recorded by the YouTube, so no problem there. But yeah, you should check that out. Okay, too late. Sorry. Okay. I want to start with a question of what a database is. I think this is foundational, not just because databases are components that we use in the systems that we build, but I think this question will turn out to be important, a little bit more deeply important even than that. But what's a database? Now, this is kind of like asking what's a chair. I don't know if you ever took like an undergraduate philosophy class, and when you talk about metaphysics at the undergraduate level, they'll say, what's a chair? And you start to define it, and you realize you actually don't have any idea what a chair is. You thought you did, but you don't at all. You just can't come up with a definition. Databases aren't quite that bad, but let's just kind of play around with this. You might say minimally that a database is a program that remembers things, right? That seems pretty uncontroversial. But then there are other programs that remember things, like the file system is a program that remembers things, and you don't really think of that as a database. So maybe there's like some kind of data model that's involved, like it's got a document model or a relational model or something like that. It remembers things and it's got this data model. Maybe that's it. Well, for our purposes tonight, I want to make this artificially more difficult than it needs to be. And I want to say that we're going to define a database as a program that remembers things with some kind of data model, and it realizes ACID transactional semantics. Now, this is not true This is not an adequate definition. This excludes things in the world that we all know are databases. But let's just work with it for now. Let's just say that we need this database thing to be a thing that has ACID transactional semantics. So MySQL with the MyISAM storage engine, suddenly not a database. A surprise to everybody. So like I said, we would not agree to this normally, but for purposes of our argument, or my argument here, I want to make things harder than they need to be. So we'll constrain this that way. Which means we have to define ACID. Now, you probably all know what the letters in ACID stand for. And oh, does anybody know it's a US game show called Family Feud? Do you know it? No, this doesn't translate outside the US. I learned in the UK it's called Family Fortunes. Also not helping. Okay, anyway, the way it works is they do a survey and they ask people things like, what do the letters in ACID stand for? And you'll get some distribution of answers. And then you have these two teams and they have to guess what the most common answer was for each thing. So you're trying to guess what people, and this would be a great thing to do at a conference, like Distributed Systems Family Feud. Because I think we would probably mostly get these things right, but I don't know that we'd agree on exactly what they mean. So it's worthwhile to talk about that a little bit. Obviously, I think they stand for atomicity, consistency, isolation, and durability. And this is what we mean when we say database transaction. We mean a database transaction satisfies these four properties. And I want to talk about these not so much in the context of a single or a set of writes to a database, but in terms of systems that we build. How do we realize these properties at scale? The conventional wisdom is you don't. Right? The conventional wisdom is you can have this if you have a single master database where there's one thread that's controlling writes, and as long as you can take locks on data structures inside that thread, you can realize these properties in a database. But at scale, you can't do it. So let's just look at what these things mean and what they mean in distributed systems. So durability. When I was a little boy, before I started doing any programming with databases, when I was learning BASIC and 8086 assembly language and these things that I did in the early 80s, durability in the databases that ran the world then, that meant that the transaction log got written to tape. Right? That was a durable database. You would take this transaction log, you'd write it off to tape, and if you had to play it back, you could play it back from the tape. Most of us would think durability means the contents of the database get written to disk. Okay, in the Family Feud game, I think that would be the most common answer. Increasingly, though, so this has already moved as a target. Its durability is a moving target. And increasingly, I think this means in a distributed data storage product that there is some kind of replication, right? You would expect that. Like if Kafka didn't replicate data, you wouldn't take it seriously. You wouldn't use it in production. You wouldn't put data in it that matters, ever. So as the target moves, I think increasingly for a system to have the property of durability, we mean that stuff gets written to non-volatile storage and it gets replicated because we want to survive when things fail. Okay, easy enough. Let's talk about atomicity. Now, atomicity, the textbook definition that we get, is always about money transfer, right? Because you have a write that adds money to my account there, and then you have another write that subtracts money from Gwen's account. Gwen's giving me $100 because she's cool. And that's how we define atomicity. That's always the textbook example. The really funny thing is, if you've ever worked in financial technology, these are all kind of old school distributed systems, and nothing is atomic, right? We say, oh, this ATM machine, it has to be atomic for this to work. Yeah, well, that's not really how the world works. But anyway, you get this, right? This is what atomicity means in terms of a database transaction. We need both of those to succeed, or neither one of them to succeed. In the context of the ordinary garden variety distributed systems that we are typically writing, let me present another atomicity problem. So you have some program there, illustrated by that blue box, and events happen to that program. And that's kind of a funny way for the Kafka guy to describe what software does. I guess it's a little predictable that I would see the world in terms of events, but it's not wrong, right? Things happen, and your program becomes aware of them. It does some kind of computation, and then what? Well, let's say you want to write things to a database. You want to remember the results of your computation. Cool. And then you've got some other thing like the recommendation engine in a graph database, and you need to write that new result to there. And also you need to be able to search, so you're going to write it to your Elastic cluster. This is all totally fine. There's nothing straw man about this. This is a thing people do. The problem is one of those things might break. And at that point now, your application has suddenly inherited the responsibility for managing what to do. Because you did the database right, you did the graph model right, what are you going to do about the search index? Do you want to go back to the database and back to the graph model and compensate those, back those out? Do you want to put it somewhere else for later? You suddenly have taken on this transaction management problem. And you don't want to do that. That's an example of the kind of infrastructure that you probably don't get paid to build. But that's a very real problem. So this is atomicity in a distributed system, and it's, again, the kind of distributed system that it is fairly commonplace for us to write these days. By the way, no solutions up front. I'm just trying to make it seem like your life is terrible for a little while. And by the way, if you build distributed systems of any kind, your life is definitely not as good as it could be. I mean, oh my God, this is my job. It's my whole team. Our job is to make using Kafka seem like a good idea and using Confluent seem like a good idea. And I'm here to tell you, any distributed system that you build is just bad. Everything that should be easy is hard. Some things are impossible, but you're probably not going to take my advice. You're probably going to keep doing it. You're not going to go get a simpler job. So anyway, this is hard, and that's atomicity in distributed systems. Let's talk about isolation. That's the I in ACID, obviously enough. Let's say we have a single shared database and two processes that are trying to modify it. And that's a recipe for disaster. If you have a single update in place mutable data store and two processes are trying to change it at once, something has to give. Either performance, usually it's performance that gives, performance has to give or correct results have to give. So let's say there are two things, or what we're trying to do is create new accounts. And process one is, let's say, a web front end, and process two is another web front end. And those are both making requests against some service on the back end saying, hey, we want to create a new user. So somebody comes to the app and they type in their name, and their name is Tim, and so they ask, is there an existing Tim? Database says no. The other process, some other imposter Tim, we all know there can be only one, but some other Tim is also trying to create an account. So that process comes and asks, is there a Tim? And they say no. And so that first process moving along in time says, all right, make me one. And that second one would also say, make me one. Now, nobody would ever build this. Okay, we're all smart enough to know that that's bad. But that illustrates the problem that we have to address. This is the isolation problem. What we want is for those two independent processes, process one and process two, up through process n, which are separate computers, their clocks are not synchronized, they're running independently, and we want their access to that single data store to appear as if it's happening in one thread. Because the magic is when it's one thread on one core, on one machine, you can lock data structures local to that thread. You can actually make things work. And so we want the accesses of those two processes to look that way. And if we build this in this naive way, we get this kind of failure where we'll create duplicate usernames, and clearly that's bad. So that's our isolation, our distributed isolation problem. Consistency always makes me wonder why ACID had to be ACID and why it couldn't be AID. Sometimes it seems like the C in consistency is like an obvious thing. And in most definitions, if you look up what people intend by consistency, they mean things like, well, after you've written to the database, it's not broken. It's like, well, yeah, of course it's not broken. Of course, why would we write a system that breaks the database? But I think a slightly richer definition of consistency is really not a property of the data store, but it's a property of the application. And we'll say that minimally, that means that the application is going to enforce some invariance or some constraints on the data, like usernames will be unique, or account balances will be greater than 0, or something like that. When we change the database, it will remain in what we call a consistent state, and by consistent we mean that the invariants we have defined remain true. This is a problem, and I'll spoil it. Our isolation solution, the consistency solution, is going to fall out of our isolation solution. We're going to fix isolation. We're going to realize, oh, that fix that we have makes consistency all better too. So anyway, I don't want to give anything else away. We'll get there. That's funny. I did this a few days ago. Where was I? I was at a conference last week, and I had a black slide. It was a different presentation. And I was on the black slide, and I was talking for a few minutes, and somebody said, hey, the screen is broken. I'm like, no, the screen's not broken. So I'm going to have to add this slide intentionally left blank so you'll pay attention to me for a few minutes thing. Anyway, these are the problems with atomicity, consistency, isolation, durability. We want to solve these with Kafka. We want to solve them at scale. It's not interesting to solve these in one thread because that solution has existed literally for decades before probably anybody in this room was writing code for money. We want to solve it at scale, and we're going to do that with Kafka. Now, you guys all probably know that Kafka stores events as these things called messages. Messages are key value pairs. We put them into topics, which is just this ordered list of events. That's the kind of primary data structure in Kafka. A topic is, by the way, if you ever hear anybody say Kafka Q, you have my permission to be annoying and say, well, actually, Kafka's not a queue. And if they get mad at you for being annoying, you can tweet me and say, Tim said this was okay. It's not a queue. A queue and enterprise message queues are infrastructure that, again, we've had for a long time, lots of operational experience running them, lots of people have experience integrating them into applications, and the key property of a queue is that when you read from it, the thing you read goes away. You don't ever read it again. You have removed it. And that's never true of Kafka. People occasionally ask me if they can get Kafka to behave in that way, to implement actual queue semantics, and the answer, funnily enough, is no. Not only is it not a queue, it refuses to be a queue. It's a log. That difference is fundamental and important. So topics are durable records of events, and they remember events until you tell them not to. So that can be forever. This can be an infinite store of, well, you need infinite storage, but time-wise, it can decide never to forget an event. And that's what makes it a log. We can read the same event over and over, and it will not go away until we tell it to. And these logs are persistent. That's very important. They're actually stored to disk, period. And we will not forget events in a log, messages in a log, until they get older than a time that we set. And that's entirely configurable. We can split these up. We can take a topic and split it up into pieces called partitions. Each one of those partitions is a log file that can get stored on a separate machine. That lets us scale out, right? Otherwise, if it was just one log on one computer, we would exceed the storage capabilities of that machine. We'd exceed the I/O capabilities of that machine. So all these things, to be able to scale, we need to split up into pieces. I think you guys pretty much know that. And we take those pieces and we can replicate them, right? That's a topic split up into 4 partitions on 4 different brokers, but we're not going to have just one copy of each partition. Like I said before when I was talking about durability, obviously we're going to be able to replicate these things so that when a broker goes away, we still have copies of the data lying around and we haven't really lost anything. So that's just kind of built in what we call table stakes of a piece of modern data infrastructure. And if there are questions, any questions on YouTube yet? All right, yeah, one? No. Oh, good, okay, all right. Interrupt me when they come up. Okay. This is exciting. I want YouTube questions. And if you guys have questions, I mean, Just, yeah.
I have a question about consistency.
Mhm.
So, do you think that consistency is related to consensus and coordination?
Yes. Yes. The question is, do you think consistency is related to consensus and coordination? So, yes, but there are two definitions of consistency at work here. So when we have consistency in the acid sense, acid consistency is not the same as the consistency related to consensus. When you're talking about consensus and coordination and consistency, that is what you might call loosely cap theorem consistency. I'm taking something and I'm writing it in a few places, and how do I know that I've written it successfully in enough places? How do I know that what I'm reading is the thing that I wrote? So that is what we'll call, I hate this phrase, but it's what I've got right now, cap theorem consistency. Acid consistency is the thing where I don't have duplicate usernames, account balances, I've got invariants that I'm maintaining. So it's the same word, completely different things. I hate it too, but I don't make the rules. Any other questions? Okay. And so we're not explicitly not talking about this, but all kinds of interesting things happen in Kafka with consistency of the kind that you're asking about. Those things are there. We're going to let them happen and just be glad that they work and not talk about them. All right, producers are programs that write the topics. You guys have probably written producers. This is code of yours, and it really just handles the plumbing. That's what producers do. They get stuff across the network, and they are in all of the languages. Java, Go, .NET, C, Python, those are things that you can get somebody to support, and there are lots of community languages that happen as well. All right, couple important things about consumers before, again, I don't want to dwell on this stuff because I know you're a fairly experienced audience, but I'm going to refer back to some of this stuff later, so I want to make sure I've said it. A consumer like this, just this one lonely instance, is going to read from all of the partitions in a topic. Remember that we can partition topics. That consumer has to consume all of those. Because this is a log and not a queue, remember I said, if anybody says Kafka Q, you have my permission to correct them, even if you have to be annoying. It's for their benefit. Because it's a log and not a queue, we can have multiple readers of a topic. And maybe you knew that. I can't stress enough that this has a lot of implications. All right, this has huge effects on the kind of architectures you can build on top of Kafka. Now that I can have any number of applications reading from a topic, I can produce to a topic, I can manage the schema of the messages in that topic, hopefully with the schema registry, so that you've got some help of keeping track of who's putting what in and whether it's in the right format and whether consumers will be able to read it. But subject to that, assuming you get schemas right, you don't need to know how many other consumers there are. You just create data, and you probably create it with some kind of consumption process in mind, but other people are probably going to have their own bright idea what to do with that data, and they get to. So that's huge. Queues don't do that, logs do. That matters a lot. That is like soil with fertilizer and water. Other software can grow in this now. So this is an absolute linchpin to building an evolutionary architecture on top of Kafka. This architectural property, the fact that that's possible. So don't ever forget that. It's a log and not a queue, and that matters. Also, as you may know, we can scale these. If there's too much work to do in one instance of the consumer, I simply add instances. And as long as I still have partitions, I can keep adding instances, and those instances get work to do. And that's elastic. I can remove a consumer, and it'll rebalance. It'll move the partition back to one of the remaining ones, and I can add one and scale back and forth and optimize my compute costs and all that kind of stuff. What doesn't work here? So somebody who's who knows consumers fairly well, that whole little thing I was saying, just like clicking a clicker, it's just that easy. What goes wrong?
Holding.
What's that?
Holding.
It's two people.
Polls. It's polls.
Polls?
Order.
Poll? No. Order. Yeah, polling is right. You said order? Yeah.
Never mind.
Okay. Well, the answer I'm looking for, you're all wrong. No. The answer, ordering is a problem if you change partitions, right? You're still, well, I mean, or you have order within a partition. You don't have global order, but you always have order within a partition. Let's just assume that that's good enough, because it almost always is. The answer I'm looking for is state. This doesn't help you with state at all, and any interesting consumer is going to be stateful. So that sucks. We're going to have to fix that, because usually you're going to be aggregating or enriching or doing something where you remember something about a message that you've seen before. Oh, I was going to say, do I need to pose here? But no. Yeah, so when you do that scaling, if you're just using the consumer library, like which is like Kafka assembly language, it does not help you with state at all. Okay. Horizontally elastically scalable if stateless, and only if stateless. So this is cool. There are some other things, though, that you would be tempted to enhance. If this is, and there was a time, by the way, when Kafka stopped here. It would be a shorter presentation in like 2013 or 14. I'd be done. And I couldn't talk about any other Kafka features. And you would have to go build them. And early adopters did. I always think of Yelp, because they were an early adopter, and before any of the other cool components of the platform existed, they had to write them. And that's bad, because that's not your job. For example, you'd say something like, well, there's this database out there, and I want to get changes from the database into a topic. And you think, I can just write that in an afternoon. I'll poll the database every second. I'll query for a higher ID than the last one I saw, and if I see it, I'll write that row into a message in a topic. Right? Easy. Yeah, some smiles, like it's not that easy. And then you do it again for another table. You just copy and paste the code, deploy it again. Right? Third time, you're like, I'm going to write a framework. Why? Because frameworks are fun. Because nobody tells you how to do it. You're the boss. There's no business stakeholder that tells you that on Tuesday you have to send 2 messages and Wednesday you only send 1, and all that kind of stuff, right? Well, as my friend, software architect Admiral Akbar says, that is a trap, because you never, when you're tempted to write infrastructure like that instead of code that delivers business value, you never get there. You never get to spend the time that you want. There are always bugs you can't fix. There are always features you can't add. You always end up with a buggy partial implementation of the thing that should exist, just because of the nature of business software. Which is, the Kafka community has recognized these things and made things like Kafka Connect. Kafka Connect is that thing I just described. So if you don't know about it, you do now. When you've got Kafka in the center of an architecture, that's cool. You're writing streams jobs and integrating with all kinds of systems. It's the arrows that are the trap, right? Those integration points are things that business people would call not differentiated. There's nothing about your integration with a database that's any different from a competitor's integration with a database. So you have a tool like Kafka Connect to help with that. The idea is, in a declarative way, you take a connector that exists in the community. Some connectors are commercial. Sometimes you pay for them. Many of them just exist for free. You take that connector, deploy it to your Connect cluster, take a little blob of JSON that looks like that, post it to the Connect server, and Connect starts reading from the database, right? So you declare what you want to happen. You don't write code for connectors that you don't have to. We have had a hackathon going on upstairs today where there was some Kafka connecting happening. At least I'm told. I recommended that there be some Kafka connecting happening. I haven't seen the demos yet. We'll find out. Anyway, and this gets you out of writing a bunch of code because there's a whole bunch of connectors out in the world that you don't have to write. And if you do have to write something, then it's cool. It's not that hard to write a connector. Did you guys write a connector today? No. Okay. All right. Anybody using Kafka Streams? Anybody not heard of Kafka Streams? Okay. Anybody heard of Kafka Streams but pretty new to it? I think that's most of the hands. Okay. It's also a test of who is willing to raise your hands. Yeah, Victor, have you ever heard of Kafka Streams? Okay, so Kafka Streams lives in there. The consumer library is a library where you subscribe to a topic, and when a message shows up, you get the message, and you declaratively do things with the message. All the API gives you is just, here, take the message. But if you look at what actually goes on in consumers, there aren't that many unique kinds of computation. I mean, everybody's consumer is different, but only a few things really happen in there. Like, sometimes you take a stream or a topic, and there's messages in that topic where the key is some unique identifier, and you want to be able to look up that message by a key. You can't do that in a log. All you can do is scan a log. But what if you want to be able to do a key lookup on these unique keys in the topic? That's like turning a stream into a lookup table. People do that with topics. People will consume from one topic, and there'll be some field in the message that they use to go look up something from a REST endpoint, a REST service or a database or something, and then add that stuff to that message and produce it to a new topic. We always call that enriching. You might also call it joining. It's like joining a stream to a table, right? People do that. If you just talk to people who build stuff with Kafka and ask them what their consumers do, that's one of the things that emerges. People aggregate. They want to average or total or do some more sophisticated kind of aggregation or run some ML model or whatever. I would call that an aggregate. That's a thing that people do. Sometimes people join streams. That's kind of weird, but this is what happens. And people want to do it at scale. And remember, the consumer API gives you no help with doing this at scale. So this is what happens. Kafka Streams is an API that does this stuff. That's the short story. It is a Java API that does this stuff. So if you are writing code in Java, that's super good news for you. If you're not writing code in Java, well, learn. No, there's another option. But Kafka Streams is a Java API. Gives us these nice high-level abstractions rather than being like the consumer API that says, here's a message, take it, start writing stuff. Kafka Streams gives you a higher level of abstraction. So a topic becomes a thing called a stream. And if you want to group the contents of that stream based on some key, well, there's a method for doing that. If you want to filter that stream and you provide a lambda that describes the filtering semantics, well, you just pass that lambda into the filter method, you get a new stream out. If you want to run an aggregation on a stream, well, the result of that is going to be a table. Well, now you have a K-table object. So it feels more like functional programming than getting beaten, which sometimes using the consumer API. If you're doing anything fancy, using the consumer API feels like getting a beating. Also, the state problems, I will not elaborate on this, but if you will just trust me, the problems with scaling a stateful consumer, Kafka Streams solves. So if I add a node to my Streams app, an instance to my Streams app, the consumer group rebalance is going to cause partitions to get assigned to that new instance. The state that had been associated with those partitions on their former instance will move over. If I lose a node, that state will have been persisted into a special internal topic in Kafka, and when that gets rebalanced, reassigned to another instance, I get that state back. So the state problems are solved, and I will literally wave my hands about that.
I have a very deep slide about this one.
Good. Victor has a deep slide about this because I am not going deep. Let's let Victor do it. So those things, this is the other cool thing, is a lot of the time you want your stream processing not to be this some special program that you deploy over there, but if you're writing a microservice and you want to enrich it with stream processing capability, you want that in your program itself. So Kafka Streams is a library. It is a Java library. And so all of that stuff I just described is happening in process. It does not happen on a separate cluster. You deploy that code exactly how you deploy your own Java code. Streams has no opinions about how to deploy code. So if your deployments are really lame, it does not judge you. If your deployments are really awesome, it does not get in your way. So that's Streams. All right, yeah, Java API does all those things we need, locates your stream processing within your application, scales just like a consumer group, but handles state. And finally, KSQL is like a layer on top of Kafka Streams. Sometimes Kafka Streams is, in fact, a lot of the time Kafka Streams is what you want. If you're writing small programs in Java and you want to give them stream processing capability, or if you want to write all of your stream processing code in Java, even if it's a very large and profoundly scaled out kind of job, Kafka Streams works great. If you're not a Java shop, or if there is no program that the stream processing would even want to live with, you just write a query in a SQL-like language and run it on a KSQL cluster, and this query will continuously consume messages from the source topics and produce messages to a topic. In this case, that first line that says create table movie ratings, by default that will create a topic called movie ratings, and every time a new rating comes in, all that computation will run and a new result will be produced. That's KSQL. Anybody using KSQL? We can still be friends. That is the good news.
We still have some job to do here.
We do, Victor. Our work is not done. That's good. I'll have a job tomorrow. Anyway, I made a big point about how Kafka Streams is a library and just runs in context of the application and scales with your application. KSQL obviously doesn't do that. It's not a library. It's a process. And so you run a KSQL server, or it can be a cluster of KSQL servers. I mean, you can horizontally scale them, just like you can horizontally scale a Streams app. And you submit your KSQL queries to that cluster. There's a REST interface, there's a command line tool, there's various ways of doing that. You can have them start up from a file. If you already know all your queries, you can just have them start and run like that. And they will continuously consume from their input topics, produce to their output topics. Those queries just run, which actually is an unsettling thing. The first time you type a select query from the KSQL command line and you get a few results back and you don't get a prompt back, it feels broken, right? That means the query is broken. What index have I not created that I need to create? And this is going to take 3 hours, right? Well, no, it's a streaming query, so it never finishes. And the business has to shut down or something. Something very bad has to happen for there not to be any more events. So this process is happening continuously. Any questions about that before we move on? Somebody should ask a question so I can drink water. Yes, sir.
Said that the queries keep running during the select. So if you're doing some aggregation, how does the result updated?
The question is, I said the queries keep running. I gave the example of a select. So if you're doing some aggregation, how does the result get updated? Well, the query gets essentially compiled down into a Kafka Streams application. And that's an implementation detail that you don't really need to know, but just take that. And as a result, a Kafka Streams application is always a consumer and probably a producer. In this case, let's say it's a consumer and it's a producer. So it consumes from some topic, maybe some other topic as well, makes a table, does a join, groups, collects a bunch of stuff in memory over a window, and 5 minutes is doing aggregation and all that stuff. But every message that comes into that source topic, from that source topic, causes that computation to run and changes the aggregation. If you could imagine computing a count, so you're grouping by a key and counting. Well, every message you get has some key and is going to increment the count of that key. And so every time a message comes in, we will produce a message on the output saying, hey, the count for this key is now 15. So it's constantly running, constantly taking input, constantly producing output. There's a much longer answer to that question, but that's the simple one. It's a great question because the concept of a continuous query is not a thing that we're used to. You kind of have to get used to it. Streams and tables is another toughie. Victor, are you going to talk about streams and tables? No. Streams and tables is really hard. We can't help you. All right. Any more questions? That's all good. But if you recall, we were talking about ACID and databases and slightly distributed applications. Well, let's go through those 4 properties of ACID that I defined at the beginning. And I defined them and explained the problems in terms of commonplace distributed systems that you might be building. So, durability. Kafka satisfies this trivially because the partitions are replicated log files. Right? They're files on disk, and they're not on disk on just one machine. They're on disk on several machines. So, done. That's I think a fairly simple checkbox. Kafka does that in a way that is responsible for modern infrastructure. Atomicity. Remember this? This was the atomicity problem we had, or at least the one I'm going to address. We didn't want our poor application to be responsible for managing atomicity because that's a lot of work that doesn't help you be different from your competitors, doesn't help you get the sprint done, the business stakeholder off your back, the whatever it is that you're doing. So what we're going to do is this. Instead of writing to those 3 things, we're going to produce that write to a Kafka topic. I'm sure if you're surprised, you shouldn't be. So, of course, there's a Kafka topic in there. So what we do is we produce that to a Kafka topic, and that produce of that one message is atomic. There's nothing you can do to keep that from being atomic. Once we've written it, then those 3 arrows down there are Kafka Connect connectors. So they will consume what we produce and write them to the database and the recommender engine and the Elastic cluster. We keep producing, and Connect keeps consuming and writing to those 3 sinks. Now, in terms of cap consistency, this is an eventually consistent system, right? Remember, there's ACID consistency and there's cap consistency. This is absolutely eventually consistent. And we really see that when one of those sinks goes down, when the search cluster goes down. Well, I can't keep writing to that. As an application, I don't care. I'm just producing messages. I keep producing, and for those sinks that are still up and running, Connect keeps up and keeps those updated. Connect will remember where this left off, though. It's got that offset stored, and so when Elastic comes back up, it can catch up. And so service is degraded. Things, when things are broken, but from an application perspective, you don't manage atomicity. The system manages atomicity because you produce to that topic, and Connect does the consuming. So that's how we solve atomicity. Isolation. All right, this is a little different, and we're going to need some Kafka Streams to fix this. We're going to write a stream processor using Kafka Streams to fix this problem. This was our trivially broken user account creation system. What we're going to do is we're going to replace that database with Well, a log file, yes, if by log file you mean a Kafka topic, which is like a very carefully managed distributed log file. Now, the processes don't really get to create anything. And think of those as like instances of the mobile app or instances of the web front end. You know, there are a million of those. And they know who they are. They'll have a little unique ID about them. But they don't get to create users. They get to ask for a user. All right, so that first one, I'm creating my new account. There's the username form, and I type in Tim, and we want that to turn green or red, depending on whether Tim is available, right? So all I can do is ask, and so I'm going to produce that request. I'm going to say, hey, process 1 has asked for Tim. And, well, somebody on some other instance of the mobile app has also asked for Tim. So you're producing these demands on a username or requests to create a username. Now, those guys are waiting. They have asynchronously asked, and we'll have to talk in a minute about what they do to know whether that was successful, but they're waiting, and that's, at this point, an asynchronous thing. So, what is going on in here? Well, inside that drum, that's actually a stream processor. So that's a little Kafka Streams application. And it is consuming from those username requests and creating a table of actual usernames. So it'll consume, and here are people who exist. We have Vic, we have Eva, we have Ale, and now we want there to be a Tim. So it's going to consume from that topic and pull that oldest message, and it created a Tim. So now there is a Tim. And when it consumes the next Tim, it's going to say, well, no, there's already a Tim. I'm not going to make you. But remember, the front end needs to turn the box red or green to let me know whether it has succeeded. And my expectations are quite synchronous in terms of using the interface. And in all of the arguments I can make for why you should make the back end asynchronous, one thing you must not let me say is, we'll just have to teach users to expect things to be asynchronous. No, right? You don't get to do that. That's the expectation is synchronous, and you will meet that expectation. So you fake it. Those processes are going to ask, right? They're gonna say, and they're not going to ask, is there a Tim even? It's going to be, did my Tim get created? Is there a Tim created by me? And that process can effectively poll at some acceptable rate there, asking the stream processor. And so I submit my request, and then I start asking, is that there? Is that there? Is that there? And that polling, which sounds dirty and annoying to all of us, I hate it, certainly. I learned to write software writing firmware, and we knew that polling was the worst thing you could do, and you should always block and never poll. But the fact is, there's a lot of polling in the world, and the impedance mismatch between my synchronous expectations and the asynchronous nature of the back end has to be matched somewhere, and it is that polling that matches it. Okay, so that front end is saying, did my Tim get created? Did my Tim get created? Whose Tim got created? And at some point, the Tim gets created, and they find out. And these requests are serialized, so there's no possibility of a race condition. They're in a Kafka topic, period, and they will find out which Tim won and turn their box red or green, and you can't ever have a duplicate.
Yeah. How do you gonna know when to stop polling?
The question is, how are you going to know when to stop polling? When you get tired, and that's always a problem, right? If you're polling, you need a timeout.
There's a chance that after you got tired, the stream did its job.
Always, correct.
So what are you gonna do? Leave it?
Yeah, so in this case, you just have to think through the case, right? In this case, I will, after, say, a minute, that's actually a really long time, I'd probably go less than a minute, I'm creating an account, so I have to think about how long is somebody going to watch the little spinny thing before they get tired, and I should tell them, that something broke. So let's say 30 seconds. I think 30 seconds is good. I just made that up. I'm going to pull for 30 seconds, and then I will say something went wrong, sorry, try again.
Yeah, but if after the 30 seconds it did happen and your stream application did register team, next time the user gonna try, he's gonna see that his team exists. So that's the most confusing use case for a user.
It is not, because what would happen is the same application would ask to create a TIM again. So it would produce that request into the topic. The stream processor would not create another TIM because there already is one from process 2. But then process 2 would start asking, did my TIM get created? And it would see, oh, it did. So effectively that request is idempotent. And so the second time, since we had some network problem the first time that caused me not to see that it was created, the second time it will. And this is going to vary. I mean, just talking through this one, that happens to be idempotent. We get it for free. It's not that bad of a case. It might be harder in other situations, but you just have to engineer the timeout and how to handle idempotence on the request for whatever the thing is that you're doing. But you poll and you time out. And I don't present polling and timing out as some joyful activity. It always kind of sucks. But again, here everybody wants synchronous. Here everything is asynchronous. You got to match it in the middle. Question there.
Yeah, when process number 1 is calling the database and asking about presence of team, how does it know whether
Presence
it's
of
its
team.
own team that was created? Or
Yeah, the problem with that this should be clearer, but there are a couple things that I just didn't put on the slide, and that's nobody's fault but mine. This question is really, is there a TIM2? And there's an ID here of whose TIM got created. It's not just TIM, but it's TIM from process 1 that won. So that context is carried through. And that again is just this specific example. Other situations you might play different games, but that is the game that you play. It's a particular TIM from a particular requester, and that requester, as long as it always knows who it is and always gives that same ID in the request, everything's fine. Consistency comes out in the wash. We just showed how we keep the unique username invariant true in this case. So again, that tends to fall out of our isolation solution. So we did it. We have ACID. I don't know if everybody was persuaded. We can talk afterward if you weren't, but I want to make just a couple of concluding observations here. And I think a picture of an onion is the best way to do that. I was so mad when I realized that's plastic rosemary. Like, how hard is it, Mr. Stock Photographer, to get some actual rosemary? Like, I don't think it's that hard to find. Anyway, and I wouldn't even know where to go to get plastic rosemary. Like, I could fairly quickly source some real rosemary. I'm so mad about that. I need to make my own picture. Anyway, if we would think for a moment about databases, and you can just think of Postgres or whatever your favorite database is. Databases are a little bit like onions. If you look at the outer layer of a database, it's an API, right? Say SQL, which is a great API, and I don't want it to change ever. If you peel that layer away, underneath it you find, I'm going to say, tables, right? Tables are super cool. They have constraints, they have types, they have indexes, all kinds of things that they do in relational databases. They are good, and I'm glad they exist. If you peel tables away, what do you have? You've got don't get there yet. You have some kind of storage engine, and you've only been there if you're a DBA. You do that, or you've had some very dark experience that you don't like to talk about, where you know, like pages and B trees and the update in place goodness of a database. That's all. Underneath that, you have a log file. At the center of every database is a log file. Because reading a log file sucks, we build all this other stuff on top of it. I would say arguably tables in a relational database are like materialized views, these customizable materialized views of the things in the log. So when you look at systems that we build, say this is a ordinary, very trivial, microservices thing, some e-commerce system. Somebody places an order. There's a service that validates those orders, and then it produces those validated orders to a topic, and then the shipping service consumes those orders. Right? It knows, oh, there's an order. Let me ship that, and it talks to whatever it does to talk to the warehouse. Well, that's not quite done yet, because where does it ship it? Well, the user creates a profile with an address and preferences and stuff, and so there's some service that kind of babysits that, and every time a user makes a change to his or her profile, the user service would produce that as a message to a topic. The key being the ID of the user and the value being the user profile. Well, that sounds kind of like what Kafka Streams calls a K-table. Right? So we can keep a little in-memory key value store of users. You can actually, if you do that thing where you produce changes to the user, to this topic down there, so that the key is the user ID and the value is the user record, you can, it's a one-liner to make that into an in-memory, lookupable hash table, a K-table. Also, since you've got that topic, you can reproduce that table everywhere else. You can make a local copy of that immutable data in any other service. So, we've got databases. They've got SQL, they've got tables, they've got storage engines, they got a commit log. And the table is kind of like a materialized view of what's in the log that you build to satisfy the constraints of your data model and performance guarantees and all that kind of stuff. These services are kind of that same thing. They're like tables. They're like these local materialized views of data that expose some API out to the world and satisfy some performance guarantee you want to make. So this whole idea of building systems on top of Kafka with ACID transactional properties gets at, I think, a deeper architectural principle, which is that when we build microservices on top of Kafka, it's not just microservices. It's like a database turned inside out. It's not one big system that talks to a database. The system itself is a database. And now we know it also has ACID transactional semantics, which is pretty cool. So, thank you. I don't know if we take a break here. I don't think you get a break. If you do, it's 5 minutes tops. But that's up to Ori. Victor. All right.